The first part of so question one is basically a series expansion, which is it's sort of going to rehash this Peierls argument and the idea of the existence of a phase transition in the 2D Ising model. D greater than 2 Ising model. And then question 2 on the back is the Jordan-Wigner solution to the one-dimensional transverse field Ising model. So the existence of the critical point. This will take some work, especially question 2. But you can find it in essentially like in standard books. So these any textbook or on quantum many-body theory will have essentially the solution to assignment 1 question 2. But what I'm asking you to do is basically follow the steps the way I have them laid out. Yeah, let me know if there's any questions with that. But I'll after I do basically today and part of Thursday's lectures, we'll look at the assignment again. It's been like a week and we haven't even talked about quantum mechanics, so we're going to start that today. What we're doing is we're looking at the phase diagram for the transverse field Ising model. With h over j on the vertical axis, and t over j on the horizontal. And we've argued for the existence of a critical point at some value of which we've called Tc in the classical model. And what we're doing now is we're looking at the t equals 0 limit, okay, and that phase boundary separates a ferromagnet from a paramagnetic phase, right? Where the expectation value of the sigma z operator is 1 here and 0 here. So now we're going to argue for the stability of this phase as we turn on the transverse field, but we're going to do so at the 0 temperature point. Okay. And as soon as we put on the transverse field, this sigma z operator doesn't commute with the Hamiltonian anymore. So we have to use some sort of perturbation theory. So all we're going to do today is assume that we're in the small field limit, and we're going to perform a standard perturbation theory on the transverse field Ising Hamiltonian. So we're going to use non-degenerate perturbation theory, assuming that we're starting from the ground state of the 0 temperature classical model. And we'll assume spontaneous symmetry breaking so that we can begin with a many-body state. That's the tensor product of all sigma z up. And the degenerate state, we'll assume, goes to 0 because we have some small symmetry breaking field, H parallel, which goes to 0 from above in the thermodynamic limit. Okay, so this is our starting point for the perturbation theory. And all we have to do is break up the Hamiltonian into, a H naught and an H prime, or whatever it's called. And the H prime will be the transverse field. This is my transverse field. it's a sigma x operator. I'm going to operate on the ground state. This will be my h prime in perturbation theory. So I can just write it as spin raising and lowering operators. Sigma plus and sigma minus. Okay. So these act directly on the sigma, what I'm calling sigma tensor product ground state. Okay, so recall your perturbation theory. H naught, which is this term, applied to the ground state. Okay, so gives you this Ising equation, which is just the classical energy of the Ising model, of the d-dimensional Ising model. So it's what we derived last time, minus ndj, where d is the spatial dimension and n is the total number of spins, or the total number of lattice sites. We're on a lattice. And this thing here we'll call, I don't know, phi naught, for use in perturbation theory. And remember what perturbation theory is? It's writing out the desired Ising equation, the desired eigenvalues, as this ground state energy for the classical model, plus higher order corrections. And similarly for the wave function. So the ground state wave function, psi naught, which is essentially what we desire, is written as the unperturbed state plus, I'll call them delta phi's. And in perturbation theory, what you do is you equate right-hand side and left-hand side up to specific orders. So this is order, this is order h. This is order h squared. This is order h. This is order h squared, and so on. So you build up your perturbation theory like that. And the first thing you can do essentially is look at the equation for the first order correction to the energy. So if you act on the ground state by h prime, which is this part of the Hamiltonian, so that's just raising or lowering, in this case lowering with this operator, the spin at site I. And there's a sum in that Hamiltonian. So I'll write it like this. I don't know what. I flipped spin I somehow here. Which means that if I apply a ket to this, that's the ground state wave function of the unperturbed case, then I'm going to get a first order energy correction that, because this is an orthonormal basis, just gives me 0. So that's the energy correction. So it's a fairly good hint that as I start, in this point on the phase diagram and perturbatively look at the evolution of the energy, say, as I increase the transverse field, that there's no sort of change in the state. There's no energy change. It'd be more precise to look at the order parameter. In order to look at the order parameter, I'd have to do the same sort of many-body calculation, except I would need to know the, say, first-order correction to the ground state wave function. I would need to know this term so I could calculate the expectation value of sigma z. So we can do that. That'll directly probe whether or not there's a broken symmetry perturbatively to first order in H. Okay, so the first order, what do I call this thing? Delta phi. E1 minus H prime, phi naught. That's your perturbation theory to first order in the perturbation, which is H. What is a state? Well, the state's essentially, H prime applied to the ground state wave function. So then H naught applied to this state. Just gives you the ground state energy plus that energetic gain due to that droplet. Remember, the first excited state is like a minority droplet of size 1, right? So it's E naught, and the energy is raised. This is minus NdJ. And it's raised by 2D for the hypercube times 2J for the energy gain per bond. Then I can essentially write the first order correction to the ground state wave function by just solving that equation for delta phi. Something like that. And this will give me psi naught which is just like the unperturbed ground state, so all spins up. And, okay, so H prime applied to essentially this excited state, right, normalized by E naught minus H naught applied to that state. So I need the sum. And then there's higher order terms, order H squared, which I'm neglecting here. Okay, so just standard perturbation theory. What we're trying to do is calculate the expectation value of sigma z using this. So So it's an operator, so it's sigma zi. And the way I use that is to psi naught sigma zi, to sandwich it in here. Like that. Okay, so we need to take the state. We need to operate on it by sigma z. We need to look at the normalization. So just remember when you're doing perturbation theory, that psi naught is basically given to you by that. So it's unperturbed, first order, plus higher order terms. I'll just write it up to order phi squared. Okay, the higher order terms now will be order h cubed, or h to the fourth. And this will give us something like h over 4dj. Sum over I, sum over j. We'll call this one I. This one j. Plus higher order terms. And this inner product only gives a non-zero result when essentially I is equal to j. So even though you have a double sum here, there's only one instance, say for the outer sum, where when I equals j that you get a non-zero contribution. So that just gives you a factor of n. Times n. So that's really the many-body contribution to this type of perturbation theory, just that factor of n. Why is the wave function non-normalized? Have you seen that before? Because in perturbation theory, you define this object to be normalized. That's where this one comes from, right? So this is every time you do non-degenerate perturbation theory, this is basically what comes out of the normalization of the full ground state wave function. Is it's only normalized up to corrections in the perturbing field in this case. Okay, so it's just a weird thing about perturbation theory. That's just the denominator, right? So the numerator is that expectation value. Psi naught, sigma zi, psi naught. Okay, you get many terms here. So you'll get the 0th order term. I'll write a few of them out. psi naught. Okay, yeah, that's that one. So psi naught here. Okay, those are like that's like the 0th order. That's like the 1st order in H. Let me write the 2nd order down here. Okay, so if I have this one, I need the square here, plus the square here, sigma z, oops, psi naught. What am I missing? 1, 2, 3, plus higher order terms, something like that. So all these expectation values end up looking like just sigma z applied to either, say, the unperturbed ground state or the state with one spin flipped, right? So every time you see something like this, where the two states aren't the same, you get 0. This one is non-zero because you have both the bra and the ket have a spin flipped like this, right? These ones are 0. And we're neglecting higher order terms. So only this one contributes. Oops, sigma. Great. Which is, looks like this. It's h over 4 dj squared, double sum. Let's see, I have an I in there, so I've got to be careful. I'll call them j and j prime. This is spin j flipped, sigma I. And this is j prime flipped. Okay, so these indices, I, j, and j prime. And I only get, number one, I only get non-zero contributions when j prime is equal to j. But whether or not I equals j matters. Because like when I apply this sigma z operator to the many-body state here, right? I get +1 if it's any of these spins, unless it's j prime, right? So this thing will give me something like 1 if I is not equal to j prime, but 2 if it is, or sorry, -1 if it is. So I subtract 2 off. I can write it like this. Maybe. Yeah, let's go with that. And then the same state back. Right? Makes sense? So in the end, the contribution from this term, 2nd order in H, 4dj on the bottom. Okay, and again, I basically get a delta function between j and j prime. Right, it only contributes to the expectation value when both of the same spins are flipped in the many-body states in the bra and the ket. So I get an n from that, n minus 2, basically. So the only thing left is to convince yourself that the expectation value, as written here, remains non-zero as I move up away from the axis here. So this is what I'm looking at here. So sigma z, expectation value. Looks like this over this. Write this as 1 plus this h squared term times n, say minus 2 times the same term. You can convince yourself that it looks like that. So 1 is the unperturbed value for this expectation value. This is the perturbation, right, which is basically second order in h. When h is small, it's just what we're looking for, the fact that this symmetry breaking, this is the order parameter for the broken symmetry in the ground state, where you're seeing that that thing survives with the inclusion of a non-zero transverse field. So we're almost getting an intuition for this phase diagram. This ferromagnetic phase somehow survives perturbatively because of this argument. And the only question left is whether or not, what's the phase boundary look like? Whether or not it terminates, or maybe it goes up forever like this. So what you have to do to determine that is maybe look at perturbation theory in the other limit. You might start with a large h and treat the Ising term perturbatively and see if that ferromagnetic or paramagnetic phase wins at infinite h. So that's probably a more fun problem, actually. It's actually starting in a state that's off diagonal with respect to the sigma z operators, the Ising model. So I won't do it, but if you did that calculation, you would write the Hamiltonian. Basically just in the other order. So transverse field, and then Ising term. And you would need to determine what the ground state wave function associated with the unperturbed case is. So that's just the many-body state written like this, but each one of those things is the eigenvalue of the individual sigma x operators, right? So I don't know, you could write them like this. Maybe that's weird. Each one of these is a basically up plus down state. So you write it as the tensor product. This is going to suck. I guess you can do it like this. Up. multiplied out to n, and this is just the tensor product, which I could write like maybe like this. So that's really your starting state for the perturbation theory. No, it should be I and I. Sorry, not I and J. And then you just do the same thing. You calculate sigma, the expectation value of sigma z. I'm not going to do it, but and I'll leave it as an exercise. But the expectation value of sigma z, you can show will be 0. And this is actually true to all orders in perturbation theory. So I'm less interested in doing this rigorously than basically just convincing you that you can use perturbation theory on many-body states. And all you have to do is keep track of essentially, the many-body wave function and how the Hamiltonian operates when you do this type of perturbation theory. The thing you're going to do on your assignment is a way more sophisticated calculation that'll show the existence of basically this phase transition on the t equals 0 axis, but it's specialized only for one dimension. Whereas the thing that we're doing here is for d greater or equal than 2. So, okay, so for the transverse field Ising model, we have a critical temperature. And what I'm arguing with this perturbation theory is that essentially we have two regimes. A small h regime, where the ferromagnetic phase remains undestroyed. And then we have a high h or large h regime, where this is the ground state. This thing has the expectation value of sigma z is 0. So this is part of the paramagnetic phase, which is just the name we've given for it. This point here is your first quantum critical point. And what a quantum critical point is a phase transition, essentially a second order or a continuous phase transition that exists at 0 temperature. So regular phase transitions are mediated by fluctuations in temperature, right? Basically, when we did the Peierls argument for the existence of this phase transition, which is why I'm saying d greater than or equal to 2, by the way, the Peierls argument is the argument that convinced us that there's a balance in the free energy between the entropy and the energy of these minority clusters. Essentially these things. These droplets proliferate, they grow bigger and bigger when we're in the paramagnetic phase. But at some point in d greater than or equal to 2, there's a phase boundary here. And the existence of that phase transition is essentially mediated by temperature fluctuations. Okay? And if you take 705, the critical theory, the Landau-Ginzburg-Wilson theory of that phase transition, you see exactly how it's mediated by the temperature fluctuations. In the quantum axis, we don't have any temperature, So it's essentially quantum fluctuations that give us the existence of that critical point. That's nothing you can see here. I've just argued for the existence of these two phases. But when you do your assignment 1, question 2, you'll look at this critical point in more detail. And so for d equals 1, which is your assignment, the phase diagram looks something like, or it should look something like this, where you just have a sort of one-dimensional region of ferromagnetic phase embedded in a larger paramagnetic phase for finite temperature. And so what you're going to be doing on your assignment is just looking at this axis here. So you'll derive the exact position for that critical point in one dimension. And you'll use this Jordan-Wigner transformation. So you'll transform the problem from an interacting spin problem to a non-interacting fermionic problem, which is the Jordan-Wigner problem. And the last part of that assignment, the very last question, asks you about the degeneracy of this region of the phase diagram, or this region here. And that degeneracy is related to Majorana fermions. So once you explore that in the assignment, we'll talk a little bit more about these Majoranas. And unfortunately, an exact calculation of this phase diagram is impossible. So the equivalent of what you're doing on assignment 1 is impossible for any dimension higher than 1. So we have to either use approximate techniques or perturbation type theories or numerical techniques in order to sort of elucidate this phase diagram. Okay, so that's just a bit of perturbation theory and sort of discussing this phase diagram. I'm not going to sort of belabor this point because I think any of you guys could do sort of equivalent perturbation theory and deduce these types of arguments. So what I'm going to turn to now is our first calculation of the classical to quantum correspondence for the transverse field Ising model, okay, which is sort of the baby step towards building the path integral representation of quantum mechanics for the many-body case. So any questions on any of this perturbation theory nonsense or this phase diagram? We'll come back to this several times in this class. So we're looking at this from, yeah, I can hear you. Right, so I haven't proven that. All right, so I haven't proven that here. You can have a phase boundary that looks like this. Okay, so I'm just telling you what the answer is. Yeah, so we haven't discussed sort of the existence of this. And I don't think we will necessarily. I'm mostly interested in quantum mechanics, so when we do the assignment, you'll just be looking at t equals 0 strictly. Okay. So why, when you apply a transverse field, sorry, what? Don't you get a paramagnetic? So what you do is you get a ferromagnet in the, you can't see this other board. Oh, thanks guys. You get a ferromagnet in the sigma x direction, right? But what closer to the mic, please. I couldn't hear you. Oh, yeah, so I'm just calling this the paramagnetic phase. Just because it's paramagnetic in sigma z. Yeah, sorry. That's yeah, okay, that's a yeah, so I understand. Yeah, so it's I mean I just somehow assumed we're staying in that same basis. Yeah, that's a good point. If you rotated the problem to the sigma z basis, it'd be essentially a classical problem, right? Just a classical ferromagnet in that direction. And that illustrates one of the issues with these. Why is this model quantum, right? It's only quantum in the case where you have operators that don't commute. So when either you have two terms in the Hamiltonian that don't commute, or you're calculating an expectation value of an operator that doesn't commute with the Hamiltonian. Right, so it's a paramagnetic in that perspective. So that's a good question. It leads into this whole question of classical to quantum correspondence for these types of models. So let's look more closely at the full Hamiltonian. So not really thinking about perturbation theory anymore, but the full Hamiltonian that has non-commuting terms. And from it we'll derive the quantum to classical correspondence for the TFIM. And not to leave you in suspense, so what we're actually doing here is deriving an expression for the transverse field Ising model's Hamiltonian, which in d dimensions is written as, again, the angle brackets on this sum tell me that I'm dealing with nearest neighbors. Oops. So IJ means nearest neighbors on the hypercube. And those are nearest spatial neighbors, which is weird to say, but if you have a two-dimensional lattice, you have site 1, 2, 3, I don't know. This bond is given by that index. That bond's given by that index. So what we're going to do in the quantum classical correspondence is relate this spatial model that has non-commuting operators. So we're going to relate this to a d plus one dimensional classical statistical mechanical problem, basically. And we're going to eliminate the operators. We're going to eliminate the description of this as a Hamiltonian. And we're going to have a d plus one dimensional stat mech problem that turns out to just be another Ising model. So it would be a d plus one dimensional classical, interacting Ising model with a Hamiltonian that looks like this in the extra dimension and doesn't have this non-commuting operator in it. And so we have to find a way of getting rid of that sigma x. And that's the essence of this type of classical to quantum correspondence that exists in path integral formulations. So the problem with these types of models is that the partition function is hard to evaluate when these two different terms of the Hamiltonian don't commute. Otherwise, if we had access to an easy way of evaluating the partition function, we could just solve the model. We take the trace, we solve all the equilibrium stat mech properties, just like we do with classical physics. By hard to evaluate, I mean, I want to take this trace, oops, beta, but I can't just take this trace as a sum over, I don't know, sigma z basis states or something, because there's no common basis for the two terms. I'll write my transverse field as H1 now, not H prime, because I don't want to consider it a perturbation anymore. Okay, so that's H naught, that's H1. So the simplest way to derive the classical quantum correspondence is to use something called the Trotter decomposition. Who's heard of the Trotter decomposition before? Okay. So let me go through it from scratch. So the Trotter decomposition is a way of breaking up essentially the partition function into small pieces that commute up to some error. Okay? And it's used, yeah, so anyone who's done quantum Monte Carlo has seen this, because this is one of the conceptual ideas behind quantum Monte Carlo. And all quantum Monte Carlo is a way of taking a quantum Hamiltonian in d dimensions and representing it as a classical partition function in d+1 that you can then associate weights or probabilities to configurations and therefore do Monte Carlo. So the Trotter decomposition is the sort of conceptual idea behind that. And we're looking at a trace. Remember, a trace is like a sum over diagonal matrix elements in some basis. And we're going to take that trace, every element in that trace, and rewrite it by defining, I'm going to call it epsilon and m, where m is just some big integer. Okay, so I've taken my inverse temperature, beta, and I've divided beta up by m. And epsilon is just the size of each one of these decompositions, if you will, or divisions. I'm going to fix the temperature. So that when m goes to infinity, epsilon goes to 0. So the finer and finer I chop up my inverse temperature, the smaller epsilon gets. So now we're going to use epsilon as a type of perturbation parameter. So there's my trace. E to the minus beta h. So let me write it as epsilon h. Let's see, beta over epsilon. Sure, why not? And now I'm going to assume that I have this very large integer formally, and just write the Taylor expansion of the exponential. So this is approximately equal to 1, minus epsilon h plus higher order terms in epsilon And my Hamiltonian is simply written as the sum of two terms here. I'll call them H naught and H1. So that's just minus plus higher order terms. Right, and so this is the Ising, and this is the transverse field. And then I can essentially factor that expression into two terms in a product. So that, let's see, e to the minus epsilon h
So why can you do that?
Well, you can only do it up to an error, number one, which is epsilon squared. But what this is, right, so this is just, you have 1 plus epsilon, oops, h naught. What's going on with my h's? Or minus, did I say plus or minus? Minus 1 minus epsilon h1. Right, so the first term gives you 1. This times this gives you this second term. This times this gives you the third term in there. So you're just making two exponentials. And so the answer to your question is you can't do it if you don't want these types of errors floating around. Okay? But what we're doing is formally taking epsilon to 0. Okay? So it's just a sort of formal trick that we're using. Which, by the way, is how you define any path integral or any field theory. So, or any QMC, or essentially any classical way of treating quantum mechanics uses this. Of course, there's more refined, you can go higher orders and do all sorts of stuff, but we're just basically looking at this object now. So the partition function is just approximately equal to the trace over, and I'll just drop those higher order terms in epsilon. And I need something else. I need an M, right? Here. Okay, so I've neglected so once you have this, you imagine you have basically, m products of these exponentials, and you have a trace over that m product that is like a diagonal, the sum of all diagonal matrix elements. And then what you do is you insert resolutions of the identity in between every instance of that product. And that's basically how you derive the path integral. And we'll do that like 20 times in this class. So remember what the resolution of the identity is. It's like the most complicated way of writing 1. It's the sum over the states. So let me be explicit here. So I'm going to work on the sigma z basis, which I was just calling sigma before. So it's the sum over the set of all sigma I, which take the values plus or minus 1. That's your spin up or your spin down. And then sigma I Yeah, that's right. That's like the many-body state that I wrote last time. Sigma I. Okay, so let's use this resolution of the identity. Does that make sense, everybody, by the way? It's the same resolution of the identity that you would see in few body quantum mechanics, but it's just the set of all, the many body states exist there, right? So it's just the outer product. So I've had an operator. I'm tracing over an operator, right? I'm going to also write it in that same basis. So I could write it in the same notation. Sigma I equals plus or minus 1. All right. So let's write our partition function Z. Oops, not beta, epsilon, h naught e to the minus epsilon h1. So that the trace sigma I God, okay, so there's m of these. And let's see. Right, and the trace is the sum over those diagonal matrix elements. And in between every one of those m products, it's like this m here, I'm inserting the resolution of the identity here. Okay, so now I have basically m or m minus 1, if you will, of these types of sums, right? And I have to bring those m minus 1 sums out front in addition to this sort of product of m operators. So I'm just going to be explicit about this right now, and eventually we'll replace these products of sums and stuff over what's called functional integrals. That's basically what a functional integral is. So let's label, okay, so we're going to be concise about our labels here. So we're going to label, I'm going to call this imaginary time position. So each one of these arrows is a position of this M product expansion, if you will, where resolution of the identity exists. So I can label each one of these orange arrows with a variable I'm going to call tau. So this would be 0, this would be tau equals 1, tau equals 2, and it would go all the way up to beta. There's beta of them.
But you said there were m of them.
Oh, yeah, sorry, there's m.
Or like m minus 1 of them or something.
Right, so there's beta is epsilon times m. Right, so there's m of them, but it's of size, let's say beta equals epsilon m. So I'm gonna label them by, now do I want to label them by m or beta? Good question. What did I do in my notes? Nothing. I'm safe. So let me label them an m, which is the integer number. And because it's a trace, this state here, which I'm just writing as psi, is the same as this state here. So we're periodic in that sense. Question?
Shouldn't be epsilon on the expansion instead of beta?
Oh, shit. How many times did I write that? Okay, that's only here. Yeah, each one of these is epsilon. Yeah, sorry. Yeah, I haven't done anything except write out that. Thanks. Okay, so I have a label for this position. And because the trace is the sum of diagonal matrix elements, this and this have to be the same. That's the definition of diagonal. Okay, and I'm going to label, so I'm going to call this tau. This would be tau equals m. This would be tau equals 0. So if my unit of expansion is 1, that's right. But if I want my unit of expansion to be epsilon, which is actually what I want. So I'm going to change this to beta. So I'm just going to label the imaginary time position. Just remember that beta equals epsilon m. So I'm just going to write my tau in units of epsilon. I think that's the way I want it. Otherwise, things will be screwed up much later on. So I'm going to call this the expansion direction. So this labels this is your d+1 dimension, by the way. So what we're doing here is deriving the extra dimension for this representation. Okay, so the partition function, let me start collecting things. There's all these sums that come from all these resolutions of the identity. So it's a product over all, say, m. And I want to label this with tau. So it's going to be tau. This will be tau. So it's a product of all tau. There's a sum for each one of those things from the resolution of the identity. And there's going to be another product over tau that's this product in here. So sigma I tau plus epsilon. E to the minus epsilon h naught, e to the minus epsilon h1, sigma I tau. So I'll start counting from the right. Okay. That's kind of bulky, but that's the partition function. Okay, so why do I start at tau and go to tau plus epsilon, tau plus 2 epsilon, tau plus 3 epsilon? That's these insertion points. Okay? And so what you're imagining doing is taking these operators here, operating on sigma at tau 0, and evolving it into the next tau plus epsilon. And there's m minus 1 of those insertions, basically. So these products go to m. So it goes from beta epsilon m equals 0 to beta equals epsilon m minus 1. So right now we haven't really gained anything because we still have operators in this H1 which aren't diagonal in this basis. So the last sort of step of the path integral, if you want to call it that, of the classical quantum correspondence is evaluating each one of these matrix elements. And when you evaluate those matrix elements, if you can get an expression for the matrix element, a real number or something like that, you've eliminated all the operators in the Hamiltonian at the expense of this really complicated, sum, this functional integral or whatever it's called here. Okay, so let's look at this generic matrix element. So let me just relabel my sigmas. So forget the identification of tau and tau plus epsilon is in this expansion direction. Let me just generally take some sigma prime. Remember, it's the many-body state. So let me take sigma prime as the bra, just sigma as the ket. And generally, these can be different states. And since you have an off-diagonal operator here, you know they have to be different states. Okay, so let's evaluate that matrix element. So that matrix element let me write it like this. I just remember there's a sum in the Hamiltonian there. And the classical piece which I've written here because the classical piece commutes with the basis. With sigma z, and this is basis states written in terms of sigma z. I haven't put z here because that's just how I define things first day. Question?
Yeah. Sorry, could you explain again the going from the line where you're inserting all the identities to the line under that? I'm having trouble understanding why we don't get the same matrix elements n times since we're inserting the same identity in between all of these identical operators.
You don't get the same. So it depends on the trace is written as a sum over all states. So you start with sigma tau equals 0 in any state that is an element of the trace. Okay, so it could be a state with one spin flip somewhere, on site J or something like that. So then you operate on it with this Hamiltonian, and there's an off-diagonal piece. So generally, you can change that basis state, and that'll be changed once for this product, but it doesn't give you back the same sigma tau naught, tau equals 0. It gives you some different state, basically, generically.
Okay.
So just because of that fact, you have to propagate that all the way somehow through. And so every starting sigma, gives you a different, sort of propagation of the state all the way through. I mean, it's you can write it out for a couple simple states, basically, like a couple two-body states, maybe. But generally, it's not the same matrix element every time, right? So this is tau equals 0, and this is tau equals 1 or whatever you want. I guess I'm not labeling my taus, my integers and my epsilons are all screwed up. But and then if you do tau equals 1, tau equals 2, it's generally a different matrix element because the states are different. Yeah.
Sorry, when you say propagate, do you mean that all of these matrix elements are multiplied in one sequence, in one specific sequence?
Yeah. Yeah. So just like it's written here, you're operating by all of these operators on states. I could have written an intermediate state that was like something like trace. Okay, so that's my trace out here. Okay, so I'll do a sum. So sum over sigma. You can imagine sigma, I don't know, beta. Then the operators, sigma beta minus epsilon, sigma beta minus epsilon. Right, so that's one insertion of the resolution of the identity, and the operators again. Beta minus 2 epsilon, beta minus sigma, beta minus 2 epsilon, and the operators again. All the way down to beta equals, or 2 epsilon equals beta or whatever, all the way down to sigma 0. And then you have another sigma 0 there. Okay?
And that's just one of the sequences.
That's a sequence, but you have a sum over all possible starting states there. So that's your trace. Yeah. And you can imagine it as, we're going to maybe derive it more directly later, but this is the Feynman path, right? So if you have, say your trace is all possible configurations, but you can imagine this sort of as, say one of these things was, a bunch of spins up and one spin down. maybe that's your diagonal matrix element. You could say, well, that spin down is the beginning of a world line. Okay, so let me draw what's happening here. So you have spin. This is your basis. I've just tilted this thing by 90 degrees, but let me not do that. Let me draw it like this. So these are your starting and ending sigmas. And let me label that spin, which is for some reason here. This is your downspin. This is diagonal, so this is your downspin. What the operator sequence generally does is do things like flip around the position of that spin. And it could give you a world line like that. Or it can actually, depending on the conservation rules, so depending on the symmetry of the Hamiltonian, it could start and end world lines within there and so on. But what's happening is, you're basically, this is like a Feynman path integral. It's like the two-slit experiment where you're shooting a particle through some system. You're evolving it, but it's not through time. It's through some other expansion direction. But now you have to integrate over all possible starting points of that particle, which is like the trace. So, the next element of the sum might be something that looks like that. I don't know. Right? So philosophically, it's the same as a Feynman. It's the same as a Feynman path integral. And we're just writing it formally in a different way. So we'll see more of that interpretation later. So right now it's just kind of keeping straight the notation, right? Question?
So for two particular starting and ending points, you're not going to sum over all possible paths, right? You basically are, because you have a many-body Hamiltonian in between. So like every single one of these H1s is a sum over all possible terms. Oh, right.
Yeah. And that's this thing here. So let's look at what this looks like. So let's keep moving with this. I'm going to call this thing generic matrix element. Let me call it big X. That's equal to this thing. So the difficult part is H1. And everything commutes for the Ising part, because that's the basis we chose. So what we need to do is evaluate I don't want to call that X. I just want to call that part X. That's the full generic matrix element. Let me call this part X.
because I don't think we're going to get done today. So this is the expectation value of essentially the transverse field Ising component of the Hamiltonian. So if we can figure out what that matrix element is, we can rewrite this path integral, if you want to call it that, as something essentially completely classical. Okay, so this has a sum in an exponential. So you're going to get a product. And let me just write the basis states. I'm getting sick of these curly brackets. I should use J or something here. Maybe I'll just get rid of those. You know what I mean. So the way this is done, this type of expectation value is evaluated quite often in sort of condensed matter partition functions. So the trick to doing it in this Ising basis is you just write out that exponential in terms of a hyperbolic cosine and sine. And that'll simplify things quite a bit. So I have this product, let me call it a product over C sigma prime sigma. So this is just some 2 by 2 matrices. And expand the exponential to get those C's. I's, J's, J's. That J doesn't really matter. I'm just treating single site operators now. So the reason you do this is because sigma x has some simple eigenvalues. So you either get a plus or a minus 1, regardless of, you always define a function of operators through its Taylor expansion or something like that. So you can imagine just expanding out cosh and sinh, you would get like 1 plus sigma x squared, and then you would get something like just sigma x plus other higher order terms. Right, and since the eigenvalues, so then when we take those operators and you sandwich them within this inner product, this bra and this ket, you'll get functions of terms that are even or odd in the eigenvalues plus or minus 1, right? So here you get 1 plus x squared plus x to the fourth and sigma x to the fourth, and every one of those sigmas will give you an eigenvalue of plus or minus 1, but they're always squared or higher order or sigma x to the fourth. So it's basically an odd function. So no, even. And sinh is odd. So you can take the values of the eigenvalues of sigma x and use them to rewrite that operator as occurring outside. And I labeled it J, but this one's even. So actually this is just the identity operator. Right, and then sine hyperbolic sine, epsilon h. This one's odd, so it matters which sigma you use. And so let's write it like that. Oh, I'm writing I's now. These are all J's. Okay, so it's just a trick that's used often in the cases where your eigenvalues are plus or minus 1. So you see it all the time in these types of Ising models. So that 2 by 2 matrix sigma prime sigma is hyperbolic cos when the product is 1, and when the product is minus 1, it's hyperbolic sine. Okay, so this is basically the last step in writing the matrix element. And in order to finish my goal of writing a full partition function in terms of a higher dimensional Ising model, I just want to massage this into the form of the partition function for the Ising model. Okay, so I have something here that I can evaluate in terms of the sigma z basis. So this is kind of the crucial step in transforming things to be diagonal, right? But it occurs at a cost. And so let's use this to write a matrix element. We'll see that cost. Okay, so I want this thing to be some coefficient exponential, some coupling constant, which I'll call K2 for a reason, times sigma prime sigma. Okay, so now it looks like an Ising element of the partition function, but I have to solve for A and K2. But solving is easy because I have two equations and two unknowns. Plus and minus for the exponential. Right, corresponding to these two cases here, the product sigma prime sigma is 1, or the product is minus 1, so that's 1 and minus 1. And I can use some trig identities. To write A like that. And similarly, I can solve for K2. And I'll just write it down. Because really, it's not interesting. What's interesting is that I can write that 2 by 2 matrix C is basically an exponential with sigma prime and sigma as the argument. Okay, so let's just write our generic matrix element. Let me write it out in full notation. So it's sigma I prime. Remember, it's these two exponentials. And sigma. And these represent some tau and some tau plus epsilon. Okay, now I have to insert the expression for that full matrix element I called X. Okay, so this thing here. So it's a product from j equals 1 to n. So the product of all these different a's, but they're all the same. So it's a to the n. Okay. And then I have my, I have my diagonal piece and this off diagonal piece, which is now written in a diagonal way using this expression here. So then I just have an exponential, and it's this coupling constant. There's a sum there. And let me write K1 is just epsilon j, just so this looks similar. But the form of the sum is different. And this is just epsilon j. Okay, and I'll write the full partition function next time, but the point is that the crucial piece of the, path integral is figuring out this matrix element and writing it in terms of something that can be evaluated in that basis that we've chosen. And so these couple tricks here, right, which maybe aren't a priori obvious, but just breaking this thing up into two terms, one that can be written as, just a scalar times the identity operator, or a scalar times sigma x, allows us to just evaluate, the expectation value of sigma x in the sigma z basis. Okay, gives me these two terms for the two different cases. So basically, if there's only two possible cases of this product. And that allows me to write it as an exponential that gives me this Ising term here. So next time, we're just going to plug this in back into the partition function, which, you can do yourselves. It's not that hard. But what you're seeing here is that this is an equal time. This is an equal space, different time Ising term. Okay? So I have two indices here that are the same. Okay? So they're in the same spatial position, but remember what this prime meant. This prime meant the difference between, say, tau and tau plus epsilon. Okay? So that difference is what I'm calling imaginary time. So this might be tau. This might be tau plus epsilon. But this term has no tau dependence in it. Every one of these terms occurs at the same tau slice. So this is equal time. Equal. We'll see later why I call this time. Okay. So when I plug this into the expression for z, I'll have a d plus 1 dimensional lattice model, and I'll have an equal time piece, and then I'll have an equal space piece at different times. Okay, so we'll finish that up next time, and we'll draw out this partition function in full. Yeah, so sorry I went over, but I think that matrix element is basically the crucial step in deriving all of these path integral representations. So we're almost done with the transverse field Ising model. Start looking at your assignment. Your assignment deals with the transverse field Ising model ad nauseum. So you'll be able to look at this quantum critical point exactly in one dimension. We're going to move on to second quantization in the next class or two. And we're going to start constructing the path integral for bosons and fermions. and also the spin coherence state path integral. So we're going to see this derivation done in a couple more ways with basically different, different representations of quantum operators. Okay, that assignment's due in 2 weeks. If you don't have it, look on the Dropbox. I uploaded it there this morning. Okay? See you guys Thursday.